So this afternoon, I just want to talk to you about thermochemical conversion of biomass, and then to use the Cool Planet process as an example of that, of what's going on there. They have a particularly interesting version of that that relates not only to making biofuels, but also connects to the biochar work that you heard Francesca Catrufo talk about last time. Excuse me, there we go. All right, so this, I hope, is maybe somewhere in your memories from the talk I gave this summer on the real basics of biomass conversion to fuels. And just we can take whatever part of the biomass, we have different ways of converting it biologically, thermally, and chemically to make fuels. And there's a lot of different pathways by which we can make a lot of different fuels. But today, the focus is on that middle part about using high temperatures and chemical reactions to turn biomass molecules into fuel molecules. So this is just a little bit about kind of the topics I'll run through if you want an orientation to that. But I wanted to do some chemistry basics having to do with fuel chemistry, because that becomes important to understand what they're actually doing in the Cool Planet process, as well as what other companies are doing. So to begin with that, a little chemistry background, I'm going to tell you about different classes of organic chemical molecules that are in fuels. These are hydrocarbons, all the ones we're talking about, which means they have just carbon atoms and hydrogen atoms. And they come in different families. The first one that I'm showing you here are the alkanes. And that's where you see all single bonds between the carbons and the hydrogens. And it's just the number of carbon atoms that gives them their name. So octane has 8 carbon atoms. And sometimes they're straight, and that's what the N means in their name. So N-octane is a straight chain of carbon atoms with hydrogens around them. And sometimes they're branched. It's the case of the one at the bottom, which has 7 carbons, but not all in a straight line. There's also the family called aromatic hydrocarbons, and benzene is one that you've probably all heard of, but there are the other structures that are shown on the right, and these are all important. We'll be talking about those specifically when we get to the Cool Planet process. And there are some of these in fuels as well. They have different properties, and the ring structure is what makes them an aromatic compound, and that's a special ring structure that combines single bonds and double bonds. So why is this important for fuels? Well, I think everyone has seen when you go to the gas pump, you always have to choose what grade of gasoline you buy. And the difference in that grade is the octane number, and there are different kinds of octane numbers. But basically, this is an indication of how well the fuel burns. Not how much energy is in it, but how well it burns as a fuel in your engines. And so what we see is that octane itself actually has a very low octane number, a research octane number in this case. And then other of those alkanes, those straight just hydrocarbons with just all single bonds, they have higher octane numbers. So hexane with 6 carbons has a better octane number. But you'll notice that the aromatics, benzene and toluene, they have much higher octane numbers. So they're important to make your fuel burn better in engines. And then interestingly, you see that ethanol and other alcohols have also nice high octane numbers. I put down there the typical regular gasoline that we have in the US. For research octane number, it's 91 or 92. And all of you are thinking right now, hey, wait a minute, when I go to the pump, I don't buy, my regular gasoline doesn't have an octane number of 91. It has an octane number of 85 or 87 or 89. And that's because the octane number that's actually shown on our pumps isn't this research octane number, it's a different one. And it's the average of the research octane number and the motor octane number. So that brings it down a little bit. Anyway, so what you see from this is that if our fuel production process only makes those alkanes, we don't get very good fuel that we can use directly in our car engines. So we need to have a mix of different kinds of fuel molecules to get a good burning mixture for our cars. And in fact, that's what we have from regular petroleum gasoline. You see from this chart, aliphatic is another name for alkanes, and you see the straight chains and the branched versions. That makes up almost about half of the gasoline that we have. Another kind of alkane makes up another quarter or so, and there's about 25% of these aromatics, the benzene and related molecules. So our gasoline that we get is a mixture of these alkanes and aromatics. And you'll see the reason for these comments when we get to the the cool planet process. Okay, so a little bit more chemistry knowledge, terms, just to remind you about these if they're not something you think about every day. When we use the fuel and burn it, we're oxidizing it, and we're getting oxygen from the air into that molecule to release energy. Sometimes we do that with water. Combustion is, as I said, oxidation of hydrocarbons in this case. Sometimes we do partial oxidation, and that's when we get partial oxidation products from fuels like carbon monoxide instead of carbon dioxide, which is a fully oxidized carbon. And then pyrolysis is a word that we'll be talking about a lot, which is where we're decomposing a large molecule in the absence of any oxygen atoms externally. Okay, so let's first go through the gasification of biomass. And I'll show this chart a couple of times because basically pyrolysis and gasification are very closely related. We start with a solid biomass, and depending on how high the temperature is and how long we keep that biomass at that high temperature, we get a more severe treatment process and we get different ranges of products. We get some liquids and we get some gaseous molecules. And so the goal in gasification is to have it be at a high temperature for long enough we get this set of small gas molecules. And we get some others as well, but mainly we want those. And specifically what gasification produces is this product called synthesis gas, or syngas. And the molecules, the main composition of those is carbon monoxide and carbon dioxide, as well as hydrogen and methane and water vapor. And it's the carbon monoxide and the hydrogen that we really care about because they have a lot of energy. But we also get a solid carbon product, which is called coke, or increasingly called biochar. And this technology of gasifying biomass or coal or trash has been around for a long time, and it was used in the wartime as a way to get fuels for vehicles when they didn't have access to petroleum. So aside from just putting chunks, biomass into a reactor and heating it up, it's a little more complicated than that. First of all, we have to make the biomass into small parts. It's important when we have wood, and if it's not wood, then you may even have to dry it a little bit. But we have to find the right size particles so we're not spending too much energy making them into small particles, and large, but not so large that we get plugging and other sort of physical disruptions of our process. And after we heat this biomass fast enough and long enough that we get to have these small gas molecules that I mentioned, the synthesis gas, we actually have to cool it because it's very hot, and then we have to clean it because it has some components that we don't want, and that's also sometimes called conditioning. And that means that we remove impurities, the solid carbon particles, and other things. So we can use the synthesis gas directly if we wanted to. We could burn it in a power plant and make electricity and thermal energy, but that's not so interesting. We get more value out of transforming that synthesis gas into liquid transportation fuels. They have higher value, and that's a place where we need to use them. And so we can actually turn synthesis gas into a lot of molecules. The pathways for that are shown here. But I've circled in red the main one that I'll tell you about, the only one I'll tell you about today, really, for how we can take those gas molecules in syngas and make liquid transportation fuels out of them. And that's this process that's called the Fischer-Tropsch synthesis. And as you can see, what that yields here are alkanes, those straight and branched hydrocarbon molecules, all single bonds, that go into gasoline, into diesel. So this whole Fischer-Tropsch idea has been around for a long time, and it's been used industrially, again, to make synthesis fuels from the synthesis gas that originally came from coal. And it's this nice reaction that takes the carbon monoxide and the hydrogen that are in synthesis gas, and it makes this formula, which is actually an alkane and water. So it's a nice way. You go from these gas molecules to these alkanes, these hydrocarbons that you really want to have in your liquid fuels. And it's not just that reaction. There's a whole set of reactions that occur together. We have a way of adjusting the carbon monoxide and hydrogen ratio. Those are maybe details. The important thing I want you to understand is just that we go from gas molecules to a liquid fuel molecule. So that sounds great. And we've known how to do it for a long time, so you might wonder, why isn't it happening everywhere all the time? And the answer is that there are some economic challenges. There have been historically some economic challenges. It costs a lot to do this, to build the plants, and so the economies of scale are such that these plants historically have needed to be very large. So FT is Fischer-Tropsch, and gas to liquid plants is the idea of converting synthesis gas to liquid fuels. So they have to be very large, and so how do you do that, though, with biomass when the feedstock supply can't be as large as these plants need to be economical? So what researchers and companies have been doing has been working on getting better catalysts to make this happen more economically, so the plants don't have to be this large to be economical, to be profitable. The other concern has been historically, and especially with biomass, that some of the impurities in the biomass can make the catalysts lose their activity more rapidly than desired, and that also increases the cost. So that's been a very active area of research, especially as the goal of doing this with biomass has increased in importance in the last 10 or 15 years. So this is an idea about how one of these plants would look, and I apologize for the slightly fuzzy nature of it, but the idea is that you bring in the biomass, or it could be municipal solid waste or other forms of carbon, and you gasify it. There's this place here where you remove solid particles, and you do this cleanup and conditioning, and then it goes into the Fischer-Tropsch part of the system where you end up with some fuels and chemicals. There's also various other products that can be made. We can get power out of it and thermal energy. So that was gasification. Let me change gears a little bit and talk about pyrolysis. Again, just to say that this is related to gasification, and it's the same idea that we're heating the biomass for a certain amount of time, but in this case, what we end up making is this part of it. So it's not as hot and not as long, so the severity is less, and we end up with liquids, this idea of liquids and condensed oils. And that product of pyrolysis then is what's called bio-oil. And because you can make bio-oil instead of fully gasifying the molecules by adjusting the severity down, the way that it's done now is to have a medium severity process by using very high temperatures of up to 1,000 C, but only for a very short time, a second or less. And that's called fast pyrolysis. And these have been operating for a while, and they can even operate on a relatively large scale. But work's been done to, again, improve the efficiency of that and to make them more controllable in different ways. Now, one of the challenges for bio-oil has to do with the product that you actually get out of it. The actual pyrolysis oil product, if you characterize it in these different ways on the side, let's look at the comparison between this pyrolysis oil and the typical petroleum-derived oil that best corresponds to it. The first thing you see is that the pyrolysis oil has a lot of water in it. And it's not like the water's floating on top always where you could conveniently get it off. It's really very well dispersed throughout the bio-oil itself, and so it takes some work to get it out. Another thing is that in part because of that moisture and because of other components in it, it's very acidic, which is a problem for end use. And if we look at the other thing to look at here is that it has a lot of oxygen molecules in it, which again is bad because that means that the fuel is already partially oxidized, and we want a hydrocarbon that's very reduced, contains a lot of energy. Fuel oils have virtually no water. They have no acidity to speak of. They have very little oxygen content, and they have a lot more energy content, as you can see here. This higher heating value describes the amount of energy per unit mass of the fuel. So it's got at least double what the pyrolysis oil does. So if we want to really make this bio-oil into a good fuel, we have to do some work on it and upgrade it. And that's more or less what it says here, that we need to fix the pH. We have to get rid of the oxygen and the water. And what I didn't mention on that other chart is that sometimes these bio-oils have metals, which can be a problem for further use of it. So we have to take all of those problems out with various kinds of conditioning steps, and then again an upgrading. And the main kind of upgrading has this big long name, hydrodeoxygenation. And basically what that means is that we're using hydrogen and to remove the oxygen that's in that. And so just to reiterate that we need hydrogen in here, that's one of the things we have to add into the upgrading process. So that is fine, except that we then have to figure out where will we get the hydrogen from. Just to show you that using this hydrodeoxygenation actually really can work to make a nice upgraded bio-oil. You saw before, for example, that the oxygen content was quite high, and now it's low, in the same range as the petroleum-derived oil. The moisture content is now very low. They don't even list pH because it can't be measured on something with such a low moisture. And you see that it has a good energy content here, the same as that petroleum-derived oil that was on the previous chart. How does a company like Cool Planet go from maybe a research discovery on a lab bench to actually having that commercial scale plant? And why do they get to have, why should the federal government be helping them with a $91 million grant? Loan guarantee, rather. So one of the things to understand is that you don't just go make that jump in one step. So there's a number of reasons. One of the big ones is this is what you work with in the lab, flasks and beakers and test tubes. This is a small version of what a commercial scale plant would look like. This isn't even commercial scale. But you can see that the equipment is very different looking, and so everything behaves somewhat differently than it did when you did it in the first place in beakers and flasks. Another maybe less obvious reason to do this scale up, that we call it, in smaller steps is because things behave differently as they get larger. And I just put one example here of temperature control. So let's say you have a chemical reactor, and you work first on this one scale, and then you decide to make another chemical reactor, your next size of process, that's 10 times bigger. The diameter is 10 times more, and the height is 10 times more. And I should add that this process, you have to, whether you heat it or cool it, doesn't really matter, but the way that you're heating or cooling it is from the outside. Say you're heating it, and you have to have a steam jacket around that to provide the heating. So, but the reaction is taking place all throughout the volume of that cylinder. And what you see here is that your ability to actually heat or cool what's inside changes dramatically from the smaller one to the larger one. Just by increasing the diameter and the height 10 times, I increased my volume by 1,000-fold, but I only increased the surface area by 50. And so my ability to transfer thermal energy into the contents of the reactor is much, much different at the larger scale than at the smaller one. And so I have to think differently about how my processor would run. There are many other reasons just like this about why things are different as you get larger and larger. And engineers can model that and try to predict how it will happen at the larger scale, but those predictions are not always accurate, and so you risk less if you make the jump, make the size increases in smaller increments. So this is this process of what we call scale-up, and you're increasing the size and the complexity incrementally. And so the typical scales we have for that, normally we talk about 3 or 4 sizes. There's the laboratory, and the first thing you're trying to do in the laboratory is just get a proof of concept. Does your process idea work? The second thing is that you're trying to measure the rates of reactions, or the rate of heating, or the rate of cooling, and also how much you get of the products of interest to you. Because that yield, that's what helps determine whether or not your process has any chance of being economical. And the rates help tell you how large you think your reactors and your heat exchangers and so forth have to be in the large-scale process at the end. And you also want to find out how certain factors really matter for the process. So does it work better at this temperature or that temperature? What pressure should you use, etc. So once you think you have a handle on things there, then you can go to the next scale, which is usually called a pilot scale. And this is somewhere between 10 and 100 times the size of the laboratory process that you did on the benchtop. And now this is for the first time you're really putting everything together. In the benchtop, you had a beaker or a flask that you were carrying out the reaction in, but you didn't really have anything like the real process where you're cooling it and conditioning the products, etc., the other steps that you need. In the pilot, you put all that together, and now you're running the process continuously, so you have to understand how the different parts of the process interact. I mean, maybe the reactor runs best at this temperature, but downstream from that, another unit needs a different temperature altogether. You have to make sure that you've got a unit in between that changes the temperature and works well at the flow rates that you expect. And again, you're collecting data and the rates and the yields, so and trying to match it up to what you predicted from the previous scales, so that you know if your models are good or not. And you also are now producing enough product that you can send it off to a lab or to your end users to see if it's got the quality that is necessary. So from there, you can go to what's called a demonstration scale. Now you're, whereas before you might have been in a warehouse, now you're actually outside at a site that's an acre or two in size, perhaps. And now you have everything running, not just the process, but all of the supporting operations now become important. And again, you're comparing your model predictions for both the technical process, but also your economic model, to see how everything's actually going, and then finally use that information to go up to your scale at which you're actually really making the product and